As of now, the network has gone through many epochs, and the gradient descent has a good understanding of the cost function, and now it needs to communicate to the network as to how to adjust the weight and biases in a way that the error can be reduced. Now keep in mind that there are different hidden layers, and each of these hidden layers have its own set of neurons, and each of those have their own set of weights and biases. Each layer also will have its cumulative error score. As we know, in an actual feed-forward network, there could be many hidden layers, and micro decisions are made in each of these hidden layers. But the layer just before the output node, where the major decisions are made, this layer plays a very significant role in determining the network's overall guess. So the back propagation method first changes the weights and biases in the last layer, and based on these changes, it changes the weights and biases on the next consequent layer looking backwards, and hence the name back propagation. Now, the exact way how the weights and biases are calculated are based on the chain and the delta rules. So this pattern of backpropagation achieves the most optimum way to find the best fit of the parameters, which will bring the error to a minimum. All right, let's go back to the simplified version where we only have one hidden layer. Now the network knows the error. It has come up with a method to reduce the error, and also a method to communicate this error with the network. Now the next question is, how big do you want to make the change? So that is called as the step size, which is basically how big a step you want to take in the direction the error is going to be reduced. In the first pass, the cumulative weights and biases were 7, and hence the output was 7. So now the cumulative weights and biases are 6, and then the output is 6. Now you see that the change in the weights and biases is 7 minus 6, which is 1. So that can be taken as a one step, or you can take a percentage. This is as of now heavily abstracted to accurately point, but the takeaway is the step size of a number 1. So if you actually portray this on the network, so you give an input and the biases and the weights are reduced to 6, so the output is 6, and the error is reduced and it's a 5. So the step size is 1, and it's also called as the learning step. So if you continue on the step size, so next time the bias is going to be even 5, and therefore the error is going to be a 4. So after 6 iteration or epochs, now the weights and biases are 1, and hence the error is a 0. So this combination of weights and biases is what is called as a trained model. Now with this trained model, the network can guess, given a 1, it knows what the biases it should apply so that the output is 1. So in other words, the network guess matches the desired output. Now something to consider is, if the step size is for 1, for example in this case it goes linearly from 765 all the way to 0, you see that the error also gradually reduces to a 0. If the step size is 2, which is you change from 7 to 5 and then all the way down to -1, in this also the error touches the minimum, which is 0. But if you increase from 2 to 5, you see that the parameter changes from 7 to 2 and then so on. But in this case, the error actually does not reach a minimum of 0. It goes all the way till 1 and then starts to go in the other direction. So that's why the step size should be considered carefully. Too small a step, for example, if the step size was 0.1, so in that case, this would change like this, 6.9. So this would be 6.9. and then this would be 6.8, and so on. So as you can see, there'll be a gradual change in the error, and obviously you will reach the bottom, but it'll take some time. So those are some challenges with the step size. There are some more topics further down the road of optimization, which we will see piece by piece throughout the course. Thank you.